Hi. The next 15 minutes, we're going to be concerned with a question that everybody is familiar with. That is the question of playing a really, really nice card game. My idea here is to present you some of my research done at Stockholm University, where we will give you a completely new perspective on how to play cards using physics. The card game we're going to be concerned with is called Bridge, and hopefully some of you have heard of it. Bridge is one of the most popular games in the world today. It is estimated that it is played for about 200 million players around the world, and it also has an international bridge federation, and this federation is also recognized by the International Olympic Committee. So to say, bridge is quite a serious game. Well, the essential question when you play bridge, no matter if you're amateur or professional, is how do I win this game? My intention now is to present to you how the world of subatomic particles and atoms, known as quantum mechanics, can help you when you play bridge and bring your game to a completely new level in such a way that no ordinary non-quantum mechanical bridge player can ever hope to do. So when you hear this, we can make a little strange marriage here between quantum mechanics and bridge, and we want to say, okay, what does quantum mechanics have to do with bridge? Well, let's start by having a look at what is bridge. I will go ahead and assume that you guys don't know how to play bridge, and that's completely fine. I'm not going to tell you either, but I want to tell you something about the game. No, what's the point? So when you play bridge, you have 4 players, and you play in teams of 2, so north and south here are going to play against west and east. And from your point of view, you can only see your own cards, so you can't see your partner's cards. So naturally, in a partnership game, it kind of makes sense that if I could somehow talk to my partner, ask him about his card, discuss strategy, our next move, we would do a lot better game. That is kind of evident. So how do I do it? Well, I can't just go ahead and ask him, hey, do you have the diamond queen on your hand? Because that's cheating. There's a very clear rule about communication in bridge. Information may only be exchanged through the cards players put on the table. It means that if I want to ask my partner something about his hand, I have to take a card on my hand, put it down on the table, and he has to look at it and try to interpret the signal I am sending him. So bridge is not at all like poker. This is a really intellectual and advanced game. It takes weeks to learn it. That's why I'm not presenting it to you here, how you play. But we can identify this communication problem in bridge. How do I exchange information accurately and effectively with my partner? That is, how do I get him to understand what I'm saying through my cards? Well, bridge players have been playing for like 100 years or so they have tried to answer this question, because it really makes or breaks your game. It is the essence of the bridge game. Communication is of vital importance. So of course, every single bridge player having tried to solve this problem has attacked it from a bridge player's point of view. There are numerous strategies for solving it. There are pros and cons to all of them, but they have one common factor. They have all nothing whatsoever to do with physics. And this is where quantum physics is going to make a difference. So, well, what is quantum physics then? I will once again assume that not all of you have heard the principles of the strange world of quantum mechanics, so I'll give you a short introduction to that also. So to make a point about quantum mechanics, it's easier to first make a point about the macroscopic world, that is, this world that you have spent your whole life exploring. And let's point out some fairly obvious stuff that I hope you all recognize after having living such a long time in this world. Let's start with saying, where is my phone? Well, it's in my hand, right? It makes sense. What if I would tell you, okay, turn around. Now, where is my phone? Well, anyone thinking this is not a trick question would still say it's in my hand. And of course, they're right. Why are they right? Well, because nature doesn't really care if you're looking or not, right? Nature doesn't care. Nature does whatever it wants to do, and you can simply choose to observe it or not. It won't change it. So if I put my phone here and you choose to look at it, it won't affect its state. Nature is independent of observation in the macroscopic world, and I hope everyone recognizes that. The second simple principle of the macroscopic world is systems are predictable. Now, I have never really understood what the point is in science fiction, why they make such a big deal about predicting the future. Predicting the future is kind of what characterizes the macroscopic world in a sense. Say, I'm walking down the street, in like that direction. I'm going to walk with this velocity, and I'm not going to stop, not for cars or red lights or anything. Then I can easily predict where I'm going to be in 10 seconds, right? Or in a minute, or in an hour, or actually any point in the future. So I have easily predicted the future. Well, we usually don't put it in that way. We call it like planning or living or anything. But it is what we are doing. We are predicting the future. That's how all of you came here today. You knew how to get here. So why are we stating these simple, obvious principles? Well, because when you shrink the size of the macroscopic world, you go down to atoms and particles, you enter quantum domain. Quantum mechanics will break these two principles down into a completely absurd world. So you enter the quantum world, so I will take my phone again and I will shrink it down to, let's say, an electron. And say, okay, assume I found my electron right here. Then it's here not despite me finding it here, but because I found it here. What does that mean? Well, from the electron's point of view, it wasn't here until I found it. If I turn around and say, where is the electron? It doesn't have to be there anymore. In quantum mechanics, we say that it's at many places at the same time. We say that observer affects nature. That is, electron is somewhere just because you saw it there. It cares if you are looking or not. So say now I take two exact copies of two electrons, like two exactly identical electrons, and I want to measure some property. It stands to reason, if I measure the same thing on two copies of electrons, they will give me the same result. But they don't, because of the second principle that breaks down. Systems are unpredictable in quantum mechanics. It means they are random. So when I measure an electron, it's going to randomly decide if it's going to give me this outcome or that outcome. So when I measure the first one, it makes a random decision, and when I measure the second copy of the first electron, it's also going to make a random decision. And since these choices are random, they don't have to be the same. So in conclusion, in the quantum world, you can actually change nature by observing it, and you have randomness. So this nature is actually fundamentally unpredictable. It does kind of whatever it wants to do. So in such a strange world, you're bound to have some really weird effects. And one of those weird effects is called entanglement. Entanglement means that measurement on two spatially separated systems can have quantum correlation. Now, what does that mean? Let's break that sentence down. Einstein referred to this phenomenon as a spooky action on a distance, and I will try to show you what he means by that. Here we have two entangled particles. Now, what we're going to do is we're going to separate them. So we're going to send, let's say we send one to like the other end of the Earth, and we keep the other one right here. Then we choose to do a measurement on one particle. Let's say we take the particle we still have here, and we want to measure something. Now, okay, what did we say? Quantum world will give us randomness. So when we measure the particle, it's going to randomly decide what it's going to give us. But the weird thing with entanglement is that the other particle that we send really, really far away will instantaneously be affected by this. So when I measure the first particle, it instantaneously affects the other one that is really, really far away. So somehow the first particle kind of told the other particle, hey, I have been measured, please adapt by this. However, the strange thing is that there is no signal going from the first particle to the other one telling it to, hey, time to adapt by this. It somehow just knows. This is really instantaneous. There is no time difference between these two events. So this is a strange phenomenon that you will never ever encounter in your everyday life. It's not allowed, but in the quantum world, you really have it. You can measure it in the lab. But, right, so why are we talking about this? What does this have to do with playing cards? Well, what did we want to do? When we play bridge, we wanted to solve this bridge communication problem. How do I exchange information accurately and effectively with my partner? Well, the essence of the quantum mechanical bridge strategy is applying entanglement. Now, why won't we cheat? Well, we will have a scenario looking like this. So we have North and South teaming up here against East and West. And the North and South are going to be the quantum team now. So what we're going to do is we're going to share entangled particles. So we're going to give a lot of particles to North, and we're going to give a lot of particles to South. And we're going to let these particles be entangled. So why is this not cheating? Well, because what did we say? The first particle being measured does not send a signal to the other one. If there is no signal between the two particles, there is no communication going on between the particles. It means we are not cheating, right? You may only exchange information through the cards you put on the table. Well, provably by physics, you are not exchanging any information over these entangled particles. Obviously, the guys who made the laws of bridge didn't account for quantum mechanics, and now they have to pay for it. So, what do you do? Well, so our research team devised a protocol and like an outline for how to do this. So when you want to play your card, like North wants to play the diamond queen, what he will do is he will perform a measurement on his particle. It will somehow affect the particle at South's place. So before he's going to play his card, he's going to make a measurement, associate that to his hand, and put the card on the table. But why would this help you? Well, we see that if you follow this procedure that we constructed with entanglement, you will end up with this. Now, what is this? This chart has success probability on the y-axis. Success probability means your partner understands what you are doing, that he can understands the card you put on the table, and he can answer it with another card. Successful communication. X-axis, you have a wide range of scenarios in the game where you might want to use quantum mechanical strategy. So what do we have here? Green dashed line shows you the best possible non-quantum mechanical player. Now this person doesn't really exist, is a really idealized bridge player. No real bridge player gets this good. This person is basically bounded by the laws of nature of the macroscopic classical world. So you can see he's quite a good player. But the red dashed line shows our theoretical prediction of the guy using quantum mechanical strategy with entanglement. And you can see that for all of these scenarios in the game, you have more or less, sometimes less, sometimes more, significant advantage over the best possible non-quantum player by using quantum mechanics. Of course, it's difficult to quantize exactly how much advantage you have, because, well, bridge can go in many directions when you play. But obviously, you will have some advantage that will be more or less significant. But this is not important, right? Important is that we want to do this for real. We just don't want to make theory up. We want to go to the tournaments and play the game, and we want to win everything. Can you do this for real? Answer is yes. We did an experimental test in this. So we are simply taking this idea of entanglement-based bridge, and we are turning it into an experiment. So we have lasers, we use the lasers, photon particles, we use an experimental procedure when we convert them to entangled pairs and supply them to our players, that we make some kind of optical measurement. And we see, well, can we do this or not in practice? So, and the result is this blue line. The blue line, you see, is experimentally obtained, and it neatly confirms the theoretical prediction, the red line. So we show that both by experiment and by theory, you can really use quantum mechanics to play bridge in a completely new and extraordinary way, and you're not cheating by any laws existing in this game. So we guess it's now up to the International Bridge Federation to decide whether they're going to allow for this technique. I guess they won't, but if they do, you kind of have to use it if you want to compete against at least in a professional level. Or the more likely option that they choose to ban it because we're ruining their game. But I would, at least in my personal opinion, I would think that that's even more cool, because that would be the first ever everyday prohibition of quantum mechanics in the real macroscopic world. And I think that would be really, really cool. Thank you.